Hello everyone and welcome to another episode of Interstigation. In today's episode of Interstigation, we'll go over 2021 AMC2 number 9. In this problem, it states that we want to find the number of ordered pairs mn such that m and n are positive integers from 1 through 30 basically, and the greatest common divisor of 2 to the m plus 1 and 2 to the n minus 1 is not 1. So we start by looking at this. It's kind of annoying that we have, well, one side is plus 1, the other side is minus 1, because we can't really get which side is bigger, or how do we find the greatest common divisor. It will be a lot nicer if we have minus 1 on both sides, right? So that leads us with difference of squares. So we can modify this a little bit to be 2 to the m plus 1. If we multiply this by 2 to the m minus 1, we will get 2 to the 2m minus 1. Although the variable here becomes 2m, we would obtain something minus 1, and that would actually make our life a lot easier. So how can we make 2 to the m plus 1 become 2 to the 2m minus 1? A simple way of doing so is that, well, we can first check that 2 to the m plus 1 and 2 to the m minus 1, the GCD of those two. Which means that, well, their difference is 2, and by Euclidean algorithm, we can just replace that with a 2 to the m minus 1. Because if d is divisible by both of these, then d would be divisible by their difference, which means that we can just replace that by 2. But we know that this is even, and this is minus 1, which means that this whole thing is going to be odd and 2. That makes our GCD equal to 1. Now, let's take a look at our original problem statement. That is, it states GCD of 2m plus 1 and 2n minus 1 is greater than 1. Now, we want to multiply it by is the GCD of 2m minus 1 times the GCD of 2m minus 1, 2m minus 1, and the right-hand side would, of course, be GCD of 2m minus 1, 2m minus 1, because GCD is always positive, we don't have to worry about the sign of the inequality. And now, how do we combine these two? Well, we know that the greatest common divisor of those this number here and this number here are the same, the greatest common divisor is 1, which means that if there is, let's say, a divisor here that is divisible, that it also divides 2 to the m minus 1, this means that this d would not be divisible by that, which means that we could simply combine the GCDs. So this would be the product of these two, which, as I have said, is 2 to the 2m minus 1. And the other term would stay the same because there is no repeated divisors that we have to worry about. And we can keep the right-hand side. Minus 1, 2 to the m minus 1. Now, let's consider this over here. How can we simplify this a little bit? So, more generally, what if we have GCD of, let's say, 2 to the a minus 1 and GCD of 2 to the b minus 1? How can we make that easier? So, before we, straight up jump in, let's think. What would be a reasonable answer that we should expect? Well, let's see. If we have, just testing out some small numbers, maybe 2 to the 7 minus 1 and 2 to the 3 minus 1, that would give GCD of 127 and G7. obviously 127 is not divisible by 7, which means that their GCD is 1. We got unlucky there. How about let's try maybe 8 and 6. 2 to the 8 minus 1 and 2 to the 6 minus 1. Okay, then we have GCD of 255 and 2 to 6 is 64, so 63. Over here, let's think. 255, 7, 9... Well, 255 is divisible by 3, so we can take the 3 out. And if we divide, that's going to be 8, 5, and 21. These two numbers seem co-prime to each other, so our answer would be 3 in this case. Do we see something here? Well, if we have the 7 here and 3 here, 7 and 3 are co-prime. The GCD is 1, and 8 and 6 have a GCD of 2, and their GCD is 3. You can, of course, if you don't see anything, pause the video, try some other examples. But the conclusion or the pattern we should get here is if we have GCD of 2a minus 1, GCD of 2b minus 1, our final answer will be 2 to the GCD of a comma b minus 1. And let's try to prove that with induction, our best friend when trying to prove something. So, proof by induction. Now, so base case, what will be our base case? Our base case will be anything such that GCD of 2 to something and GCD of 2 to the 0 minus 1. Because if we do Euclidean algorithm, that is the last thing we would get. And here, it's obvious that our GCD will be 2 to the k minus 1, which is 2 to GCD k0 minus 1. Base case. Now, our inductive hypothesis would be that the GCD of 2 to the, let's use another variable, x minus 1 and 2 to the y minus 1 would be equal to 2 to the GCD of x, y minus 1 for x plus y is less than some variable. Let's say, I'll just use a variable that no one uses so that we don't run into problems later, say data. And here that we are inducting on x plus y so that if we have either x or y decreased, we can apply our inductive hypothesis. So our inductive step would now be, well, GCD of, let's say we can start with any number, 2 to the x minus 1 and 2 to the y minus 1. We want to decrease that value. And a good way to do so is through Euclidean algorithm, of course. And that would give you, let's assume without loss of generality, that x is greater than y. If x is equal to y, I guess that would also work. So x is greater or equal to y. And in that case, we would have 2x minus 1 minus, we can minus any multiple of 2y minus 1, and that GCD would stay the same. So we multiply by this multiple. And this multiple will always be an integer of 2y minus 1. And the right-hand side stays the same, or not right-hand side, but the second entry of the GCD. If we simplify this, we get 2 to the x minus this is also 2 to the x, because it's 2 to the x minus 1 times 2 to the y, plus 2 to the x minus y minus 1, and we keep that, which means that our GCD is, we can cancel out that, we get 2 to the x minus y minus 1, and 2 to the y minus 1. And we can apply our inductive hypothesis here to get that is equal to 2 to the GCD of x minus y minus 1. And that, if we do some kind of like notion of reverse Euclidean algorithm, we would get that it is equal to 2 to the GCD of x comma y minus 1. So our proof is complete. Now let's go back. How do we simplify the left-hand side? The left-hand side is just 2 to the GCD of 2m comma n minus 1. And the right-hand side would be 2 to the GCD of m comma n minus 1. We can add 1 to both sides. We get 2 to the GCD of m comma n. That is 2 to the GCD of 2m comma n. And this would give us GCD of 2m comma n is greater than the GCD of m comma n, because we know that our exponential function is always increasing. This means that the input is greater as well. So over here, if we want the GCD of 2m and n to be greater than the GCD of m and n, this means that there are some leftover factors of 2's in n that is not exhausted in m, so that when I multiply by 2 on m, the GCD goes higher. Which means that in this case, over here, we would need to have, well, n has more factors of 2. So let's list out, well, factors of 2. I will use V2 to write that. Well, it's not n, but, well, generally x, I guess. And we have count. So we have 0, 1, 2, 3, 4. 4 is just 16, so there's only one of them. 3, we have 8 and 24. So that is 2 of them. 2, we have 4. We have 8, but 8 is already taken. So 12, 16, plus 8, that's 20, 28. We have 4. And we have all of the leftover even numbers, 2, 6, 10, 14, 18, 22, 26, and 30. I believe that's 8 of them. And then we have all of the odd numbers, 1, 3, 5, all the way to 29. That'll be 15 of them. If you add them up, that is indeed 30 numbers. Which means that 2m plus 1 and 2n minus 1. Notice that m and n are not interchangeable. We have to have n has more factors of 2, which means that if, let's say, n has a factor, if n has, well, just 1, let's say, because just 2 is divisible by n and 4 is not divisible by n, that what it means, not divisible by n, that means that m must have 0. That is, 2 is not divisible by n. And in that case, there are 8 ways to choose n and 15 ways to choose m. So that's 8 times 15. And in general, every time you step up, you can take every number that is less than it. So it is 8 times 15 plus 4 times 23. Notice it's not 4 times 8. We can take m that is not divisible by 2 at all. So it's 4 times 23, 2 times 27, and 1 times 29. So if we do these calculations, first one is 120, the second one is 92, I believe, and then 54, 29. Just make sure you don't mess up any of the steps over here. So that is 11 plus 4, which is 15. And over here we have 2 plus 5, that's 9. 9 plus 10, so 19, 295. And that is our final answer to this problem, is 295. So that's all for today. I'll see you in the next one where we go over first number 10 and the first double-digit problem around 2021 82. And hope to catch you there then. Goodbye.